All right, let's just jump right in. We are about to take a trip deep, deep inside, well, inside everything. In this explainer, we're going to unpack the brilliant experiments and some serious aha moments that finally showed us what an atom actually looks like.
I mean, think about it. That was the exact problem scientists were up against for centuries, right? Everything we can touch, everything we can feel, it's all made of atoms. But they are so unbelievably tiny that you just can't see them. So how in the world did we ever figure out what was inside?
So, the whole idea of atoms, that's not new. It actually goes way, way back to the ancient Greeks. But turning that from just a cool idea into actual science, that took some serious detective work and a bunch of super clever experiments.
Yeah, the word atom itself actually comes from the Greek atomos, which literally means uncuttable. And for the longest time, that was the running theory. People thought, okay, if I keep cutting something in half and in half again, eventually I'm going to hit a tiny fundamental particle that just can't be split anymore. That was it, the end of the line.
But hang on. In the late 1800s, that entire idea was about to get completely blown apart. Scientists started messing around with electricity and gases, and this one particular gadget, the cathode ray tube, was about to change, and I mean literally change, how we see the universe.
And this right here, this is the device that kicked everything off. So what you're looking at is a cathode ray tube. Scientists would pass an electric current through gases inside this tube at super low pressure. And what they saw was this mysterious glowing beam, a ray that traveled from the negative end, that's the cathode, over to the positive end, the anode.
And these simple observations, they ended up being the crucial clues in this whole mystery. Think about it. The rays started at the negative cathode, they could be bent by magnets, and they carried a negative charge. This meant they weren't just some kind of weird light. No way. They had to be made of actual physical stuff, particles. This is where the English physicist J.J. Thomson comes in and just puts all the pieces together. He concluded that these rays weren't rays at all, but streams of identical, negatively charged particles. And here's the real kicker. Since he could get these particles out of any metal he used for the cathode, he realized they must be a fundamental part of all atoms. He had just discovered the electron.
And then, just a few years after that, an American physicist named Robert Millikan took it to the next level. His famous oil drop experiments managed to measure the exact charge of a single electron. Now, this was absolutely vital, because with that number, scientists could finally calculate its mass, which turned out to be almost nothing, like 1/2000th the mass of the simplest atom, just incredibly small.
You know, it's funny, the name electron was actually suggested before anyone even proved the particle existed. So I gotta ask, what would you have named this tiny, negative piece of everything? Drop your best, most creative ideas in the comments below. Let's see what you've got.
Okay, so finding the electron was a huge deal, a total game changer. But it also opened up a whole new can of worms, a brand new puzzle. If atoms have these little negative particles in them, but we know that atoms themselves are electrically neutral, well, where's all the positive charge hiding? And how is everything arranged in there?
So the leading theory at the time was something called the plum pudding model. And yeah, it's pretty much what it sounds like. They pictured the atom as this sort of blob of uniform positive charge, kind of like the cake part of a pudding. And then the little negative electrons were just scattered throughout it, like plums, or maybe a better way to think of it is chocolate chips in a cookie.
So to put this whole pudding idea to the test, Ernest Rutherford's team set up a now legendary experiment. They basically built a particle gun that fired a beam of tiny, fast, positively charged things called alpha particles, and their target, an impossibly thin sheet of gold foil. Now, based on the plum pudding model, they expected these particles to just zip right through. I mean, it's just a soft pudding, right? Maybe they get nudged a tiny bit, but that's it.
But yeah, that is not what happened. I mean, sure, most of the alpha particles flew straight through the foil, just like they thought. But, and this is the crazy part, about 1 in every 8,000 was deflected at a huge angle, and some actually bounced straight back like they'd hit a brick wall.
Rutherford's own words really capture the absolute shock of it all. He said, and I quote, "It was as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you." I mean, can you imagine? He said it was the most incredible event of his entire life. He knew right away that for one of his little alpha particles to get knocked back like that, it must have hit something incredibly dense and with a very powerful positive charge. There was only one possible explanation. The whole plum pudding model, it had to be wrong. Totally wrong. The atom's positive charge and almost all of its mass had to be crammed into an unbelievably small, dense center, a core. And that's what Rutherford called the nucleus,
which means the atom is mostly just empty space.
I mean, are you getting this? We are literally watching a complete revolution in our understanding of reality, all in just a few minutes. If you're finding this scientific detective story as amazing as we are, do us a huge favor and hit that like button and definitely subscribe for more.
So, now we have the main pieces of the puzzle, right? We've got these negatively charged electrons flying around a tiny, dense, positively charged nucleus. So let's put it all together and take a closer look at the properties of these fundamental building blocks, these subatomic particles.
This table here really lays it all out beautifully. So you've got the electron with its -1 charge and that teeny tiny mass we talked about. Then there's the proton, which has an equal but opposite +1 charge. And look at that mass. It's almost 2,000 times heavier than the electron. And finally, we have the neutron, which was discovered a bit later. As the name suggests, it's neutral, 0 charge, and its mass is almost identical to the protons.
So there you have it. This is our modern blueprint for an atom. You've got the protons and neutrons packed together super tightly in that central nucleus. That's where basically all the mass is. And then the tiny negatively charged electrons, they're whizzing around, occupying this huge region of space that surrounds that nucleus.
Okay, so now that we understand this basic structure, we can finally give a proper definition for what an atom is, and we can also start to wrap our heads around the truly mind-blowing scale we're talking about.
And this brings us right to our modern definition. An atom is the smallest particle of an element that still has all the chemical properties of that element. What does that mean? It means if you take an atom of gold and start pulling it apart into protons and electrons, well, it's not gold anymore. The atom is the complete package.
And the scale, it is just staggering. We measure atomic radii in something called picometers, and a picometer is a trillionth of a meter. So it's tiny. As you can see here, a typical atom might have a radius of, say, 100 picometers or so. But its nucleus, the radius of the nucleus is about 100,000 times smaller than that. It's almost nothing.
This analogy right here really helps bring that scale home. Picture this. If an atom were blown up to the size of a giant football stadium, the nucleus, the part with pretty much all the mass, would be the size of a single marble sitting right there on the 50-yard line. The entire rest of the stadium is just the vast empty space where those tiny electrons are found.
Which, of course, leaves us with one final, absolutely mind-bending question. If atoms, and that means everything, including you, me, and the chair you're sitting on, are almost entirely empty space, then why does anything feel solid? Why can't I just walk straight through a wall? That's a fun one to think about. Share this explainer with a friend who loves this stuff, and let us know your best thoughts in the comments. Thanks for watching.